Hi everyone, I'm Dan Fullerton, and today I want to talk to you about thermodynamics and heat engines. So, our objectives for today are going to be to calculate the maximum theoretical efficiency of a heat engine, and secondly, understand that all systems tend toward a state of increasing disorder or entropy. So, second law of thermodynamics. Heat flows naturally from a warmer object to a colder object and cannot flow from a colder object to a warmer object naturally without doing work on the system. That's kind of like thinking what happens if you have a Lego castle and you drop it off a third-story building. If you drop it, when it hits the ground, it's going to become more random. Not a chance you're going to go take a whole box, your castle Lego set, unput together, drop it from a third-story window, and when it falls, it's all going to come into the castle, and it's going to be all built when you go look at where all the pieces land. Things tend toward disorder naturally. You have to do work on them, put energy into them in order to make them more ordered. Heat energy cannot be completely transformed into mechanical work. Nothing is 100% efficient. And all natural systems tend toward a higher level of disorder or entropy. The only way to decrease that entropy, do work on it. What that also means, your room isn't going to clean itself. You've got to do work in order to make your room more ordered. So, heat engines. Heat engines convert heat to mechanical work. And the efficiency of a heat engine is the ratio of the energy that you get out in the form of work to the energy you put in. So here we have a nice little heat engine diagram where we have a high temperature reservoir. The heat is flowing out. Some of it becomes useful work, and what isn't useful work goes into the low temperature reservoir, the heat energy that comes out. As we look at this, we could analyze it to say that the work out is equal to the heat going in minus what goes into that cold temp reservoir. And the efficiency then is going to be the work you get out of it divided by what you put in. Or, since work is QH minus QC, that's QH minus QC over QH, or 1 minus QC over QH. A couple different ways to calculate efficiency. We could also talk about power in heat engines, where power is the rate at which work is done. We've talked about that before. Work divided by time. Now, if we start again with our efficiency equal to work divided by QH, we could rearrange that to say then that work is equal to the efficiency times QH. Or if we want power, that's work divided by time. If I divide both sides by time, I get EQH over T. But work over time over here, that's power. So this implies then that power equals E QH divided by T. But we also know that efficiency is 1 minus QC over QH. Therefore, power is equal to, I'm going to replace efficiency with 1 minus QC over QH times QH over T. Or with one more step, power is equal to QH over T minus QC over T. The rate at which energy is being put into the system minus the rate at which it's coming out. Now, on a PV diagram, a heat engine is a closed cycle. And if you have a clockwise process, like that, it represents a heat engine. If it's going in the reverse direction, counterclockwise, well, that's a refrigerator type system. And Carnot engines are theoretical heat engines that operate at maximum possible efficiency. The Carnot engine uses only isothermal and adiabatic processes. In Carnot's theorem, the whole point of these Carnot engines is they're theoretical engines, but you have to know that no engine operating between two heat reservoirs can be more efficient than this theoretical Carnot engine operating between those same two temperature reservoirs. So the efficiency, the Carnot efficiency, the maximum theoretical efficiency you can get is your hot temperature minus your cold temperature divided by your hot temperature, assuming, of course, that all of your temperature must be in Kelvin. So let's see what we could do with this. Determine the maximum efficiency of a heat engine with a high temperature reservoir of 1200 K and a low temperature reservoir of 400 K. Well, the Carnot efficiency is going to be the high temperature minus the low temperature divided by the high temperature, or 1200 K minus 400 K over 1200 K is just going to be 0.67 or 67% efficient. That's as good as it's ever going to get with those temperature reservoirs. Another problem, a 35% efficient Carnot engine absorbs 1,000 joules of heat per cycle from a high temp reservoir held at 600 K. Find the heat expelled per cycle as well as the temperature of the cold reservoir. Now let's write down what we're given. We know our efficiency is equal to 0.35. Our high temperature reservoir is 600 K, or pardon me, I wrote that backwards there. Our heat that's put in is 1,000 joules. We'll write that over. The heat that's put in is 1,000 joules, and the high temperature reservoir is 600 K. All right, well, let's start out by finding the temperature of the cold reservoir. To do that, we'll start with our efficiency equation. That's our high temperature minus our cold temperature divided by our high temperature, our hot. Therefore, the efficiency is equal to 1 minus Tc over Th, which implies then that Tc over Th must be equal to 1 minus the efficiency. Or Tc is equal to Th times 1 minus the efficiency. So substituting in our values, Tc is equal to 600 K times 1 minus 0.35, which is going to give us a cold temperature of about 390 K. Now we also have to find the heat expelled per cycle. To do that, let's go back to our efficiency is equal to work over our heat put in, which implies then that work is E times QH, which is equal to 0.35 times QH is 1,000 joules. I keep wanting to write that as the temperature. 1,000 joules, or 350 joules. Once we have that, the work done is QH minus QC, which is going to be, here's our QH, 1,000 joules minus 350 joules for a total of 650 joules. So the heat expelled per cycle, 650 joules, and the temperature of the cold reservoir, 390 K. All right. Hopefully that gets you a good start on thermodynamics and heat engines. If you need more help or looking for more information, check out aplusphysics.com. Thanks everyone. Make it a great day.